In this lecture, we examine function composition. There is an algebra of functions. Given two functions, for example, f of x is x squared and g of x is x plus 1, we can, in obvious ways, add, subtract, multiply, and divide these functions. For example, the sum of the functions f and g is defined simply by f plus g of x is x squared plus x plus 1. We simply add the two values of the functions. The function f minus g is f minus g of x is x squared minus the quantity x plus 1. F times g of x is x squared times x plus 1. F divided by g of x is x squared divided by x plus 1. Given two functions, x squared, for example, and x plus 1, we can divide g by f and get x plus 1 over x squared, or we can divide f by g and get x squared over x plus 1. Whatever happens, if we're dividing one function by another, the quotient is not defined whenever the denominator is 0. So g divided by f of x squared, x plus 1 over x squared, does not have 0 in its domain because that would make x squared 0. In the same way, we cannot plug in x equals minus 1 to the quotient f divided by g because that would make the denominator x plus 1 equal to 0. We've briefly introduced the sum, difference, product, and quotient of two functions. A much more important operation between functions is function composition. A more important operation between functions is the operation of function composition. In the picture below, we have the function f taking us from the set x on the left to the set y in the middle, and then we have the function g taking us from the set y in the middle to the set z on the right. So f is a function from x into y, and g is a function from y into z. Then g composed with f is a function from x into z, defined by first letting f map elements from capital X into capital Y, and then letting elements of capital Y be mapped by g into capital Z. We'll do an example or two. Notice that g composed with f is the first function involved, while g is the second. We read function notation, g composed with f, from right to left. In the example below, g composed with f first maps through the function f. So the element a from capital X on the left is mapped by f to the element 1 in the middle. Then g maps 1 to the @ symbol, so a is mapped by the composition to the @ symbol. B is mapped by f to 1. 1 is mapped by g to @ so the composition, g composed with f, maps b to @ C is mapped to 3 and then to the hash mark. D is mapped first to 4 and then to the double exclamation point. So that's the way our composition works. A will be mapped all the way to @ B also is mapped to the @ symbol, C to hash mark, and D to double exclamation point. We can view a function as a machine, taking inputs and generating outputs, as we see in the top figure. Drop in x, out comes f of x. The composition of two functions is in a sequence of function machines. Let's look at an example. In this case, when we drop in x into the function f, we get out x squared. And when we drop in x to the function g, we get out x plus 1. The function g composed with f will map 3 to 10 because f maps 3 to 9 and g maps 9 to 10. If f and g are described by an equation, then g composed with f can be described by an equation. Here, g composed with f of x is g of f of x, which is g of x squared, which is x squared plus 1. So g composed with f of x is x squared plus 1. If the codomain of the function f is the same as the domain of the function g, then we can compose first f and g to create g composed with f, or we can do it the other way around to create f composed with g. The order of composition is important. The function f composed with g is probably not the same function as g composed with f. For example, with what we've been doing before, f of x is x squared and g of x is x plus 1, then g composed with f is x squared plus 1. But on the other hand, f composed with g is f of g of x is f of x plus 1 is x plus 1 squared. So g composed with f of x is x squared plus 1, but f composed with g of x is x plus 1, the quantity all squared. Again, if f of x is x squared and g of x is x plus 1, we learn from elementary algebra the importance of parentheses, that 1 plus x squared is different from 1 plus x squared. The use of parentheses and the order of operations is especially important in the composition of functions. In this case, squaring and then adding 1, that's what g composed with f did, is different from adding 1 and then squaring. That's what f composed with g did. G composed with f of x is x squared plus 1. F composed with g of x is x plus 1 squared. In the next lesson, we will work some problems involving function composition.